I'm giving the first talk introducing you to Majoranas, and rather curiously, this conference series has never had a talk on Majorana particle, ever. So I will have to cover a lot. I'll have to cover 76 years of Majorana physics in 20 minutes. That's 12 seconds a year, but people who know me know that I'm actually capable of doing that, just speaking faster. So there are a lot of people that I worked with at various levels, and so those are the names. So let me start by telling you what a Majorana fermion is right away, okay? So I'm going to tell you what a Majorana fermion is in 3 different ways. All of them are simple descriptions, but hopefully they're not simplistic or misleading. So a Majorana fermion is a localized zero-energy neutral mode, so it's an excitation of a system, which emerges naturally as a subgap excitation in the gap of a superconductor in spinless PF superconductors. And to create this subgap excitation, of course, you need some kind of a defect. The defect could be a vortex core in a 2D system, or the surface mid-gap state in a 2D system, or 1D wire ends. It turns out that if you have such a zero-energy mode in a spinless PF superconductor, then it will automatically be a non-abelian anion. I will not talk about non-abelian anions at all. You can ask me something about it. There's no time to explain them. But these are the same non-abelian anions we talk about in 5-half fractional quantum Hall effect. So Majorana modes have zero energy. Although they're excitations of a system, they have zero energy. They also have zero charge. They're neutral. They have also zero spin. They're spinless particles. And the reason they're called Majorana is that they are their own antiparticles, which is very rare for fermions. In fact, there are no other fermions, neutralino, in supersymmetry theory, but they are their own antiparticle. And plus, they're non-abelian anions, which are suitable for topological quantum computation. So now you understand why there is so much interest in the subject. They are really very strange objects, and they're almost like nothing, but this nothing has properties which are very, very important. So one other way of thinking about it, that there is zero energy, bound, neutral, non-local superposition. I could have thrown in the word entangled there also, superposition of half an electron, half a hole. I'm talking about solid-state systems now. I'm not talking about Majorana particle of original Majorana particles of Ettore Majorana. They always must occur in pairs. Why? Because in normal solids, in condensed matter system, our everyday system, we don't get to choose our particles. Okay? Unlike particle physicists or string theorists, we cannot make up particles. We only have electrons, holes, protons. We have only what solids have. So solids do not have, or gases do not have half an electron or half a hole. So that means if you have an object that's a neutral combination of half a hole, other half and other half hole have to be somewhere else. So you can never have one Majorana by itself in a solid. If you have a Majorana here, other Majorana has to be somewhere. Now, when you're talking about Majorana, we are talking about these two Majoranas being very far from each other, ideally several miles, but in practice, several microns, okay? If you put two Majoranas on top of each other, you really have nothing, and that's just an equivalent description of solids using fermion creation and annihilation operator. You can do all of that physics using Majorana operator, but that's just a redefinition. When we talk about Majorana, we are talking about the two Majoranas are very far from each other. If the two Majoranas are close to each other, they're just an electron hole pair separated by large energy. All right, so brief history of Majorana fermion. So Ettore Majorana asked this question, that his questions was, Dirac theory was very prominent. This is mid-1930s I'm talking about. So Ettore Majorana asked the question that is it absolute must that Dirac equation must be complex? Apparently he did not like complex numbers. So his question was that, is it possible that equations for spin-half particles could be real? And the answer, of course, is no. It's certainly possible to write real solutions. You just take complex conjugate, add them. So that equation is the Majorana equation, and solution of that equation is the Majorana particles. Okay? So in this, when you do that, Majorana fermion has to be electrically neutral because you're using pure real numbers. So particle and antiparticle has to be the same. When you conjugate them, they're the same object. So it must be its own antiparticle. So Majorana realized that, and he was a bit disappointed. He realized it cannot be a description of nature, because in nature, electrons come with positrons, neutrons come with antineutrons, protons come with antiprotons. But he speculated that maybe this new object that Wolfgang Pauli was talking about, neutrinos, maybe they are Majorana particles. That's what Majorana hypothesized. And in fact, this hypothesis was powerful enough that even now people are doing experiments. There are two very famous experiments going on, one in a deep mine in Italy and one in a mine in South Dakota, where people are doing this double neutrino-less double beta decay experiment, which will prove whether neutrino is or is not a Majorana particle. This question is still open. Neutralinos of supersymmetric field theory by construction of Majorana particles. But they, of course, are, if they exist, you're going to see it from a long time. But the things we are interested in, or I am interested in, is a totally different question. I'm interested in how can it emerge in semiconductors. In fact, I want it to emerge in systems that EP2DS and MSS people are interested in. Semiconductor, 2D semiconductor system, 1D semiconductor system, things like that. So you're talking about emergent Majorana. Majorana, when you talked about this, that a particle and antiparticle are the same, let's say if neutrino is a Majorana, it will be a momentum eigenstate of the Majorana operator. Okay? It will be a momentum eigenstate. So the Majorana we are talking about are not momentum eigenstates. Those are excitations. So we are talking about emergent Majorana. So in our case, Majorana operator itself could be realized in low-dimensional condensed matter systems. Okay? So it has to be something that's emergent, because obviously we are not going to have real Majorana particles, just as we do not have real anything in solids. We just have electrons, holes, protons, and so on. So it has to be some emergent property, but how? How can it emerge in semiconductors? Well, so we are looking for a zero energy mode, because remember, Majorana has zero energy. We are looking for a zero energy mode, and throughout the talk, when others talk, the other 5 people talk, what you'll find continuous reference to zero bias conductance peak, ZBCP, zero bias anomaly, ZBA, zero bias peak, all of these things, in whichever context they are being stated, all they're indicating is there is zero energy mode in the system, okay? So the experimentalists are saying, here I'm seeing a peak at zero energy, zero voltage. It corresponds to a zero energy system, and that zero energy excitation, and that zero energy excitation is the Majorana, okay? This is the logic. Now, I want to emphasize right now that this zero energy is necessary but not sufficient. You can have zero voltage peak from many sources in a condensed matter system. So even if you see zero bias, that's the first thing. Obviously, you have to see it, but it may not be sufficient. So how do you see it in solid-state system? Actually, it's very simple. Superconductors are natural hosts for Majorana. Why? Let's take a quasi-particle in superconductor. They're called Bogoliubov quasi-particle. They are a linear combination of electron operator and hole operator. This is because superconductors have electron symmetry. So if you want to know what are the excitations in the gap of a superconductor, these are this Bogoliubov quasi-particle. So U and V are just number. If you take U is equal to V star, then gamma operator is equal to gamma dagger. So all you have to do is to find a Bogoliubov quasi-particle which satisfies the property U is equal to V star. If you find that property, that has to be Majorana, because then gamma is exactly equal to gamma dagger, electron and hole are the same. And this is magic. You say, how is that possible? Electrons and holes are different objects. It's because of this magic that the ground state of superconductor is filled with infinite number of Cooper pairs. You can take an electron and convert it into a hole. Just a Cooper pair goes somewhere in the ground state. So that's what is going on. So now our task becomes much simpler. We don't have to go into a deep mine or anything. All you have to do is go inside the gap of a superconductor and look for the situation where U is equal to V star. That's all you have to do. Well, we know what will give that. So we're just looking for that state exactly at zero energy in a superconductor. We know they will show up as bound states in vortices or mid-gap state interfaces. But the problem is fermion doubling. This is a fundamental theorem. You can call it Kramer's theorem, fermion doubling theorem, that fermions come in 2 flavors, and you always have them. So you're not going to get zero energy state. So that means if you have an electron state here, you must have a hole state here, because superconductors have this exact symmetry called electron-hole symmetry. So if you have a gap state which is particle-like, you'll have another state here which will be hole-like. But you can avoid fermion doubling if you have spinless, because of course, doubling of fermion comes from spin up and down. If you get rid of spin, there is no fermion doubling. So what you need now, we have reduced the problem just by logical reasoning. All you need is a spinless superconductor. That means it has to be at least p wave, because it cannot be S wave. The total wave function has to be antisymmetric. So if you have just spinless, that means spin polarized, then it has to be p wave. So now you have to look for spinless, effectively spinless p wave superconductor. Question is, does it occur in nature? And then once you have that, just look for the zero energy subgap state. You are done. And all of this arises from the fact that superconductors have this exact symmetry, particle-hole symmetry. So if you solve Bogolov-de Gennes equation, which is equivalent to BCS theory, then for spinless fermions, particle-hole symmetry guarantees a Majorana at is equal to 0. So if I give you a spinless PUF superconductor, you don't need to even do an experiment. There has to be a Majorana at is equal to 0. So our task has now been simplified. We need a spinless PUF superconductor. And then if you have it, then if you change some parameter, you go from a topological superconductor to a spin-full superconductor, is protected by a gap. Because imagine, by topological, I mean Majorana carrying. Any superconductor that can carry a Majorana is a topological superconductor. Don't ask me why. In 25 minutes, I cannot explain that. But this property is protected by this gap. Why? You have a zero-energy mode in this topological superconductor. Normal superconductor cannot have a zero-energy mode. Why? Electron-hole symmetry. Every electron excitation must have a holes. So that means when you go from this to this zero-energy mode cannot just disappear. How is it going to disappear? Where is it going to go? It is neither electron nor holes. So to go from here to there, you must go through a quantum phase transition where the gap vanishes. This is a fundamental theorem, and this is called topological quantum phase transition, and this is where the protection comes from. You cannot destroy the zero-energy state just suddenly. Its destruction must go through this phase transition, and this is the topological protection we hear about. You may hear it stated different ways, but this is all people are talking about. Problem is that this thing does not exist in nature, okay? We do not have spinless PUF superconductor in nature. If nature was kind and we had it, our problem is solved. This thing would be solved a long time ago. It doesn't exist, so you have to engineer it, and there have been many ideas engineering it, but I would say the most experimentally practical idea, that's why we are talking about it in this session, is a semiconductor, because semiconductor has spin orbit coupling, low dimension, you can apply magnetic field to create Zeeman splitting, and you can change chemical potential and carrier density, all those things help. So you now need to have a semiconductor which becomes a superconductor. And so the proposal we made, which kind of started this phase of the subject, the phase that we are discussing today, there are many different branches of Majorana physics. It's like a tree with many species coming and going and so on. The specific branch of evolution, Majorana evolution we're talking about, started in this paper, where we proposed that actually it's very easy to create a Majorana, very easy to engineer a Majorana. All you need is a semiconductor, indium antimonide or indium arsenide, which has strong Rashba coupling. And now you have the ingredients to get rid of fermion doubling. So what you need to do now is to create superconductivity in it. Well, that's easy also in principle. Put a superconductor on it, proximity effect will induce SOF superconductivity here. Now you have to convert this SOF superconductivity into POF superconductivity. You have to make it spinless. How do you make it spinless? You make it spinless. You cannot apply a magnetic field because it's a two-dimensional system, then there'll be orbital effect. So you then put a ferromagnetic insulator here so that it induces proximity effect and creates spin splitting by exchange. So it's a double proximity effect. Superconductivity induced by the superconductor and spin splitting induced by the ferromagnetic insulator. We worked out the theory analytically completely and showed that this system will have a topological quantum phase transition when the spin splitting, Zeeman splitting, exchange splitting, spin splitting, I'll call it VZ or VX, it's spin splitting, where it's coming from doesn't matter, is larger than chemical potential square plus superconductivity gap square root. That's all you have to do. Once you satisfy this condition, you'll have Majoranas. Remember that if you know about superconductivity, this is exactly what is called Clarkston limit in SOS superconductivity. Spin splitting larger than gap, let's put mu to be 0. We can define mu to be 0. Then VZ larger than gap means that your spin splitting is larger than superconducting gap. In normal SOF superconductor, you have nothing now. There was a very nice talk yesterday by Professor Adams on this. Superconductivity is destroyed. What we are saying, what we showed in this paper, that you have spin orbit coupling, just as it destroys SOF superconductivity, PUF superconductivity will come up. Now, I just want to mention, I will have no time to discuss it, that since you're breaking time reversal invariance explicitly by having spin splitting, you have no Anderson's theorem. So this thing is not immune to disorder. So disorder is important. Disorder will have to be discussed, and Pete Brewer will discuss disorder. I don't have time to discuss it. Now, let me emphasize also that if you make this system or system similar to it, Majorana must exist because it's being made artificially. So if experimentalists can make precise system I'm talking about, Majorana must exist. There is no escape because this is not a natural system. It's being artificially created, like BEC in cold atomic system. So what is the magic? Magic is magic of Rashba. So you create two parabolic bands. So you have a little band splitting here, and just introduce spin splitting here, and put the Fermi level in that gap. And if you do that, all you need to do is induce SOF superconductivity, you got Majorana. Because what is happening is, there is a spin is rotating around, there's a spin texture here, and at the two ends, both spin are up. It's not a spinless system, but spin-orbit coupling and Zeeman splitting together is creating effectively in 2D a chiral system, and in 1D a helical system, which is effectively spinless. So fermion doubling is avoided, you have Majorana. Oh, Charlie Marcus is online, I can see. I can see he's really paying attention to what I'm saying. Sorry about that. Actually, I did. I have never seen Charlie embarrassed. This is the first time. So the thing that I think is very nice about this proposal is that each element of it is generic and very simple. Everybody knows about spin-orbit coupling. Everybody knows about superconductivity. I'm talking about indium antimonide, indium arsenide, nothing special. Superconductivity, aluminum, niobium, Zeeman, just apply, somehow split the spin. Each element, 3 elements are all very, very, I would say, trivial. You put them together, magic, Majorana. Well, the problem is that you really want to do Zeeman by applying a magnetic field, not by a ferromagnetic insulator. That's where 1D comes in. Through dimensional reduction, we can just go from 2D to 1D. Now you can apply a magnetic field. Why? Because you don't need to worry about orbital effects anymore. Just apply a magnetic field. It's a 1D system. There is no orbital effect. So everybody realized that 1D is the place to look for experimental Majorana, because just take indium arsenide, indium antimonide nanowire, apply a magnetic field. Already there is Rashba. That will split the spin. That's what I'm showing here. Put the chemical potential here, create a superconducting gap, and you can again solve this problem exactly at the Bogoliubov-de Gennes level, analytically. And the moment that I'm calling Vx what I call Vz before, spin splitting is larger than this quantity, exactly the same condition in 2D and 1D. The condition doesn't change for seeing the Majorana. You have a topological phase transition, and so for Vx, when Vx is smaller than this quantity, you have a trivial superconductor, ordinary SOF superconductor. When Vx is equal to that, the gap vanishes, then you have. So let me show you numerical results. This is direct numerical results, not based on analytical theory. Theodore Stanescu took the Bogoliubov-de Gennes equation for indium antimonide nanowire, put it on aluminum, just solve the problem by diagonalizing the large matrix. And what I'm showing you is what happens when spin splitting is increased, gamma is spin splitting. So this is an SOF superconductor, proximity induced. Gap goes down because spin splitting is increasing. When the gap is exactly equal to spin splitting, you have Clarkston limit, superconductivity has disappeared. But if you have spin-orbit coupling on the right-hand side, gap reopens. This side is an effective spinless PUF superconductor. And these are all for different values of parameters. Let's not worry about them. Let's just look at one of them, this red one, where the gap is 0.25. So at 0.25, chemical potential is 0. The SOF superconductivity disappears. You have effective PUF superconductivity, and this right-hand side of this 0, you will always have a Majorana. Then at a very large magnetic field, the gap goes down again in 1 over Vz. So gap is equal to 0 indicates the topological quantum phase transition point. So notice the topological gap itself depends on spin-orbit coupling, but the condition does not depend on spin-orbit coupling. The topological condition does not depend on spin-orbit coupling, but the gap, how large the gap is, here are 2 different gaps. This one has more spin-orbit coupling than this one, so the gap is larger. The topological gap is larger when spin-orbit coupling is larger. In fact, it's proportional. So you do want a system with very large spin-orbit coupling, because otherwise your gap will be very small. So what do the density of states look like? These are not schematics. These are actual numerical calculations, okay? So here is what the density of state looks like in the topological phase. Here is what it looks like trivial phase. So this is literally a numerical calculation, taking Vx to be less than this when it's SOF superconductor, nothing in the gap. You don't expect anything in the gap, and there's no disorder here. If there's disorder, things will change a little bit, but the basic picture is still the same. So if it's an SOF superconductor, there's nothing. Everything is kept the same. All we do is change Vx. When Vx goes above, beautiful. At the 2 ends of the wire, this is the length of the wire, you have 2 Majoranas. You see this state? This is the Majorana state. It must be there because it's a spinless PUF superconductor, and it comes out exactly as it should. This is, you may ask, what happens when many subbands are occupied in a 1D wire? Well, many subbands are occupied. This is 1 subband occupied, 2 subbands occupied, spin polarized subbands. 2 subband occupied, you will not have Majorana. 3, you will have Majorana. So it just alternates. So you need odd number of spin polarized subbands occupied, and then you'll have Majorana. Even number, you will not have Majorana. So all these things shake out exactly as it should. This is now the zero bias peak. So the experiment we proposed is that put a semiconductor wire on a superconductor, apply a magnetic field, and then do a tunneling measurement. And it was already known that if you do such a tunneling measurement, then there'll be a peak associated with zero bias, that this peak here, ignore everything else, this peak that you're seeing here will have exactly 2 e²/h height, and this is resonant underwave reflection, and this resonant underwave reflection at zero energy, this is the famous zero bias peak, zero bias conductance peak. You're doing a tunneling measurement, zero bias peak, zero bias anomaly, they're all the same. But if you do the same for the non-topological superconductor, there'll be no peak at zero bias. The peak will be outside the gap, because that's exactly what happens. And this is a theory, and this is direct numerical work showing that indeed, when you have the topological phase, there is a zero bias peak, but the peak height doesn't have to be 2 e²/h. When you include disorder, you include finite temperature, you include the fact that the wire is a finite length, peak height could be anything. It doesn't have to be this quantized value 2 e²/h. It could be factor of 100 smaller, which is what happens in experiment. Okay? Now, I said that this is necessary condition, and at least 3 or 4 of the experimentalists will talk about it, 3 of them. A sufficient condition, or almost sufficient condition, would be fractional AC Josephson effect, which should have this 4 pi periodicity, kind of E replaced by over 2. I have no time to talk about it. We predicted this in our original paper also, but fortunately, Leonid will talk about this later in the session. So this is what numerical density of state looks like. Here is the trivial superconductor. These are each for different spin splitting. Everything else is fixed. Here is the trivial superconductor gap vanishing. This is the Clarkson limit. Trivial superconductor gap comes to 0. The moment it comes to 0, you have an effective POF superconductor, and you have this beautiful Majorana peak at zero bias, which you don't have in the SOF phase, but you have it in the POF phase. And this is the famous experimental result that Leo Kuhnhaven will talk about after me. And this is different magnetic field. This is the SOF phase. You don't see anything. That's the interpretation. POF phase, you see a peak, and this peak is where all the excitement is all about. There's a theoretical prediction, which in this particular rare case came before the experiment, but look how similar they look. And now it has been reproduced by a large number of groups, both on indium antimony, indium arsenide, niobium, and aluminum. Time has run out. So the only last thing is my last slide. So the last thing I want to show you is some other experiment. This is a very recent work. The paper just came out. Actually, the paper came out in 2013. This is wrong. The paper came out just a month ago. And it has this word, smoking gun. And if you know PhysRep and PRL editors, they don't allow words like that. So I had to withdraw the paper from PRL and publish in PhysRep, because I insisted smoking gun has to be there. And because experimentalists read, apparently, if they see the word smoking gun. So what we said, everything I was telling you is when the Majoranas are very far from each other. What happens when you bring the Majoranas close together? After all, these wires are not very long. When you bring the Majoranas close to each other, you know what happens, because it's very elementary chemistry. 2 states seeing each other, what happens? They split. Bonding, antibonding, symmetric, antisymmetric, they split. They are no longer zero energy state. There should be a little splitting. This splitting should be experimentally observable, because you don't have to change the length of the wire. If you change the magnetic field, that changes the coherence length, is the dimension length that matters. But the interesting thing that's not obvious is that this splitting will have an oscillation. In fact, the origin of this oscillation is similar to RKKY and Friedel oscillation. So we predicted this actually 2009, even before this work. But recently, Tudor-Staniscu did beautiful work for the actual experimental systems, showing depending on whether you have constant density or constant chemical potential, you should see these oscillations, and we showed what they're like. And I'm going to conclude by saying that, yes, direct observation of the splitting at high field would be a smoking gun at some level. And you have to be careful whether the experiment is being done at constant chemical potential, constant density, but that's a detail. You should see the oscillations, and voila, these oscillations have been seen at Delft, Weizmann, Urbana, Harvard. And in Delft at Weizmann, actually, these oscillations existed before this paper of ours. These oscillations are there, and have a prediction. So let me just conclude by putting this slide up without talking about it. These are the different branches of evolution of Majorana. The 5 fractional quantum Hall, chiral PF superconductor. This is something I didn't talk about. And this is where we are. We are here. Okay? This is the system we're all very excited about, thanks to the experimentalists. With that comment, I'm going to stop.
Shankar, this is for the uninitiated. So you talk about the neutrinos. So we know for sure that neutrinos are fermions, and in high energy physics at least, Majorana fermions are particles that are their own antiparticles. Now in condensed matter systems, we define Majoranas as creation operator being equal to the annihilation operator, and these have non-abelian statistics. So can you comment on the terminology that
Yes, I can. First, let me tell you, comment on the, it would be an anticlimax. Very bad terminology. We should not have called this thing Majorana, okay? But we did, so we are stuck with it. So I would say that depending on your taste, our Majorana is much more exciting than particle physics Majorana, because particle physics Majorana is a Dirac fermion. It's also a Majorana fermion. It obeys the standard antisymmetric statistics, Fermi-Dirac statistics, okay? It's an eigenstate, the momentum eigenstate of the Majorana operator, okay? So it's just its own antiparticle. That's the only interesting thing there. Our Majorana particle Majorana mode is an excitation, and as you know, for a quasi-particle excitation, statistics is not a meaningful concept, okay? So it is not, definitely not a fermion because it obeys non-abelian statistics, but on the other hand, it is not a fundamental particle. It's this entangled non-local object, which is why it's topological, it can only happen in low dimension. So let me emphasize, in case that was not clear, neutrinos are not going to be non-abelian. Neutrinos are going to be just ordinary fermions. So the terminology, we are talking about different things, and it has caused a lot of confusion in the community. Our Majorana, their Majoranas have some connection, but the connection is not incredibly strong, in my view. Okay, does that answer your question?
Any other questions? We have time for a couple more because we have a few minutes left of our half hour. Well, I guess it was extremely clear. Thank you very much.
Or extremely unclear. It's one of the two for sure.
Thank you very much.